motion happening on a four-dimensional sphere being represented in our three-dimensional space, one which you'll understand by the end of this video. Quaternions are an absolutely fascinating and often underappreciated number system from math. Just as complex numbers are a two-dimensional extension of the real numbers, quaternions are a four-dimensional extension of complex numbers. But they're not just playful mathematical shenanigans. They have a surprisingly pragmatic utility for describing rotation in three dimensions, and even for quantum mechanics. The story of their discovery is also quite famous in math. The Irish mathematician William Rowan Hamilton spent much of his life seeking a three-dimensional number system, analogous to the complex numbers. And as the story goes, his son would ask him every morning whether or not he had figured out how to divide triples, and he would always say, "No, not yet." But on October 16, 1843, while crossing the Broom Bridge in Dublin, he realized, with a supposed flash of insight, that what he needed was not to add a single dimension to the complex numbers, but to add two more imaginary dimensions. Three imaginary dimensions describing space, and the real numbers, sitting perpendicular to that in some kind of fourth dimension. He carved the crucial equation describing these three imaginary units into the bridge, which today bears a plaque in his honor showing that equation. Now, you have to understand, our modern notion of vectors with their dot product and the cross product and things like that didn't really exist in Hamilton's time, at least not in a standardized form. So after his discovery, he pushed hard for quaternions to be the primary language with which we teach students to describe three-dimensional space, even forming an official quaternion society to proselytize his discovery. Now, unfortunately, this was balanced with mathematicians on the other side of the fence, who believed that the confusing notion of quaternion multiplication was not necessary for describing three dimensions, resulting in some truly hilarious old-timey trash talk, legitimately calling them evil. It would surprise me if this approach was fully original, but I can say that it's certainly not the standard way to teach quaternions, and that the specific four-dimensional right-hand rule image that I'd like to build up to is something that I haven't really seen elsewhere. Building up an understanding for this visual will take us meaningful time, but once you have it, there is a very natural and satisfying intuition for how to think about quaternion multiplication. It won't be until the next video that I show you how exactly quaternions describe orientation in three dimensions, which is, for some people, the whole reason we care about it. But once we're able to go at it armed with the image of what they're doing to a 4D hypersphere, there's a pleasing